So this is the one and only lesson in this course looking at what we call reciprocal functions, which also relate to something called rational functions in pre-calculus 12. And so this is unrelated to the absolute value work. In this way, this chapter is a bit of a hodgepodge of a couple different things. So it's just a one-off lesson that is really, really important leading into your next course. So first, I want to talk about the graph of 1 over x. And essentially, it's a very simple idea. It's just 1 divided by some number. That's your input. Your output is whatever 1 divided by that number is. And since we haven't dealt with a graph like this before, it's always a good idea at first to visualize some points on a table. So I have a table here that has a lot of numbers on it for a good reason. All right? But that's it. It's a simple enough function here, just 1 divided by my input. And so, sorry, having a technical issue here. For this, 1 divided by x, well, if x is -3, it's 1 divided by -3, which if I decimalize it is about -0.3, well, it's exactly -0.3 repeating. If x is -2, it's -0.5, 1 divided by 2, but negative. 1 divided by -1 is -1. So I'm going to pause there and start plotting some of these points. So -3, negative a third of the way of a unit down, so roughly there. -2, negative half the way down, -1, comma -1. All right. And let's keep going. Now I start moving towards 0 from the negative side, but with lots of little steps. There's a reason for that. So 1 divided by -0.5. 1 divided by -0.5 is -2. So I'll plot that. So -1/2 over 2 down. And that's because there's 2 halves in a whole. And so what about -0.4? And -1 divided by 1 divided by -0.4 is -2.5. So I'll estimate that. It's hard to estimate -0.4, but 2.5, I don't know about there. 0.3. And so at this point, I'm just going to put these values in. If x is -0.3, I have -3.3 repeating. 0.2, I have -5. 0.1, I have -10, which makes sense again, because that means how many times does 0.1 go into one whole? 10 times, but it's negative. So, that last point I'll plot. It's getting hard to plot a lot of these, but -0.1 is a little, roughly -10, about right down there. That said, what about -0.01? Well, that's going to be -100. 0.01 goes into one whole 100 times. -0.001 is -1,000, -10,000. And so we start to notice, and you get the idea, is that as I get closer and closer to 0, my output gets larger and larger and larger. In this case, it's negative, but it's getting a larger and larger negative number, or more and more negative. There's no limit to how many zeros I could add there. I could go 0.00001 and 0.00000, and you get the idea. So I can see already that as I go down, as I approach 0 from the left, it just starts shooting down more and more and more and more and more. How far down? Well, I know it must go infinitely far down. I know it must be, just because I know there's no limit, how many zeros I could put right there, and therefore there's no limit to how many zeros would go right there, is one way of thinking about it. As I divide by a number closer and closer to 0, I get outputs that are larger and larger and larger, but in this case negative. When you divide by 0 itself, it's undefined. So my graph does not exist when x is 0. But as soon as x is a little bit more than 0, I get the exact same values as before, but now they're positive. So 10,000, 1,000, 100, 10, 5, 3.3 repeating, and so on. Which means I can get a pretty good sense about what this graph looks like. Up here, I get the exact same idea. Really, really close. The closer I get to 0 from the right, the larger my value gets. There's no limit to how close I can get to 0, so there's no limit to how high up this function goes. But then after a while, it kind of follows this, the same pattern as where it starts to get closer and closer to the x-axis. And so it must look something like this. And so what's happening here is right at 0, I can't divide at 0. My function does not exist at 0. My function is not defined at 0. but I can divide by numbers really, really close to 0. And the key idea is, although you can't divide by 0, you can divide by any other number. And when you divide by numbers really close to 0, you get outputs that are larger and larger and larger. The closer you are to 0, the larger your output. And if it's negative, it's a negative value if you're dividing by a negative value. And so I know these arrows, whether to the left or right, are going up forever. So I need to show there's a break in the graph, and yet I need to show that it goes infinitely close towards this line. And so I'm going to draw something called the vertical asymptote. I'll just make it a little bit neater here. This vertical line I'm drawing, or dashed line, is not part of the graph. It's a symbol on my sketched out graph that means, that tells you, or tells the person looking at the graph, that the function in this case never actually crosses this point, this vertical line, but it gets infinitely close to it. And that's what it says. That said, one other thing I can say about this graph is that as I go to the right and to the left, I know it must also never actually touch the x-axis in this case. I know there must be another asymptote right here. Because if I look at this, I don't care what number I put into my x. I don't care if x is 3,000 or 3 million or billion or whatever. 1 divided by a big number is never going to be 0. It can get really, really close to 0, but you can't take 1 divided by a number and get exactly 0. You can get really, really close to 0, though. And so the same thing, or a similar idea, is happening with this graph as we look at the x-axis. Whether I'm looking from the above or below, it never actually touches the x-axis, because 1 divided by a number will never equal exactly 0, but it can get infinitely close to 0. And we have here is our graph of 1 over x. We call this a reciprocal function, because it's 1 divided by, in this case, just x. The reciprocal of x is 1 over x. All right, so with that said, there's a few takeaways from this. One of the most important things being you can't divide by 0. We've seen that earlier in the course when we were dealing with rational expressions. But when we divide by numbers really close to 0, we can get infinitely large or infinitely negative numbers depending on how close we get. And yet we can't actually divide by 0 itself, but only 0. And so let's look at this. Let's look at two separate functions here. The graph of f of x, which is x minus 4, and 1 over f of x, or 1 over x minus 4. So first let's look at f of x. Nice simple linear function, a y-intercept at negative 4, and a slope of 1. Okay, easy to draw because it's a line. All right, so that's the graph of f of x, or x minus 4. OK, I want 1 over this. So how can I graph 1 over x minus 4 without just making another table of values? Well, one thing I know if I look at this graph is that when f of x has an x-intercept, which means when the output of f of x is 0, I'm going to have a vertical asymptote there. I know there must be a vertical asymptote right here. Because at that point, I'm going 1 divided by 0, the output of the graph in red. What else do I know? If I look back at my table here, there were two what we call invariant points. An invariant point is where your input and your output don't change. It's one way of thinking about it. Or in this case, where the graph in red and the graph I'm eventually going to draw of 1 over x minus 4 will be on top of each other. They don't change. They don't vary. They're invariant. And that, when you're going 1 divided by something, that only happens when you're dividing by 1 or dividing by negative 1. If you're starting with a number 1 and you go 1 divided by 1, you still end up with 1. If you're starting with negative 1 and you go 1 divided by negative 1, you still get negative 1. And so anytime my graph of f of x has an output, a y value that is either 1 or negative 1, the graph of 1 over f of x is going to go for that exact same point. And so right here and right here, I know my graph of 1 over f of x will go through those exact same points. We call those invariant points. And lastly, now I just want to do a quick sketch. Because at this point, I know that as I approach the asymptote this way, I have negative outputs. My graph of f of x is negative. The y values are negative. And as I get closer and closer to 0, though, my outputs will get more and more negative. Oh, here we got an announcement.
Call parked on 801. Ms. Mao, call parked on 801.
All right, and so I know it must look something like this, just from before. The outputs are always going to be negative, and I know it goes to that point I've highlighted in green because that's the invariant point, and I know this as soon as I get past that and I start getting closer and closer to, in this case, 4, because that's where the output is 0, I start, the closer I get to it, my outputs get larger and larger and larger, but negative. And in the positive side, same idea, just kind of flipped around. And I also know this graph will never actually touch the x-axis, because it doesn't matter what I have in my denominator. 1 divided by any number here will never equal 0. I don't care what you have in there. I don't care what output we have. You can never go 1 divided by number and get exactly 0. You can get extremely close to 0, but you'll never get exactly 0. And so you see in blue again is my graph of 1 over f of x, the reciprocal of f of x, or in this case, 1 over x minus 4. All right, let's look at this one. 2x minus 5 first. So that's the graph of g of x, and I want to do 1 over that. So first, I'll graph in red. This, again, it's a linear function, a y-intercept of 5 and a slope of 2. So up 2 over 1, or down 2, back 1. All right. So there's my graph of g of x. All right. So I want 1 over this. And again, I'll show that in blue. So one thing I know is that when g of x has an output that's 0, 1 over g of x will have a vertical asymptote. And that's right at this point right here, about negative 2.5. That's where my line crosses the x-axis. So that means that's where my line has a 0 output, which means 1 divided by 0 is going to be undefined. So I know I'm going to have a vertical asymptote there. I know my graph of 1 over g of x is going to be invariant anywhere the denominator, 2x plus 5, has an output that's 1 or negative 1. And again, those are my invariant points. So I know it goes to those points. And now hopefully you can kind of see the same sort of idea as before. It must look something like this. And then same sort of idea this way. But remember, it'll never touch the x-axis. Because again, it doesn't matter what value we're looking at in function g. You can't go 1 divided by a number and get 0 exactly. But you can get infinitely close to 0. And that's, again, what these asymptotes are showing. There we go. OK, doing that a little bit faster than last time, but the same idea. I'm first paying attention to where there's a vertical asymptote, where they're invariant, and then the general sort of shape. OK, what if we have quadratic functions in my absolute value function? OK, so I have, for this one, x squared minus 4 is h of x. So a nice simple quadratic function, a vertex 4 down, but no other stretches or reflections. And again, I can draw these 7 points really quickly, because the graph of x squared is something we dealt with a lot earlier in this course. Once you have the vertex, there's going to be a point 1 over and 1 up, 2 over and 4 up, 3 over and 9 up, and so on. All right, so I want the reciprocal of this. So again, the first thing I would do is pay attention to where h of x has an output that's 0, or really where h of x is an x-intercept. And that's at negative 2 and positive 2. So I know there's going to be a vertical asymptote at negative 2 and a vertical asymptote at positive 2 for my graph of 1 over h of x. The next thing I'd pay attention to is where is the graph of h of x equal to 1 or negative 1 in terms of outputs. So right there, right there, right there, and right there. I don't know the exact x coordinates there. I don't really care what they are. I'm just trying to sketch a graph. And so I don't know those exact x coordinates, but I can see that's where the output, the y values, are 1 or negative 1. So I know my reciprocal function will have 4 invariant points. I know it's going to go through these 4 points. And so, for example, as I approach this vertical asymptote at negative 2 from the left, I know it must look something like we've seen before, where it'll never actually touch the x-axis, but it'll be close. It'll go to that point, and then it must shoot up, but never actually touch the vertical asymptote, because you can't divide by 0. So there's the first part of my graph. And I know I must have sort of a reflection of that on the other side, because I am dealing with a symmetrical function here. And so what happens in the middle? Well, in the middle, I'm dealing with something similar, where it's got to be coming from the negative as I approach close to the asymptote. But what happens right in between? Well, if I look right here, for example, the lowest point of my vertex is -4. So the reciprocal of -4 is 1 over -4, or -0.25. So that means that point I've highlighted in blue, when I go 1 divided by it, it must end up at -0.25, about right there. I should draw that in blue, I guess. And there we go. I kind of basically essentially connect the dots. I know it's, and I have something like this. It's a pretty complex function. And I'm piecing it together again from thinking about where the vertical asymptotes are, where these invariant points are, and this general idea that as we approach division by 0, we get these hugely positive or hugely negative numbers, this sudden change. But again, what I just sketched out in blue is a very accurate graph of 1 over h of x, or 1 over x squared minus 4. And I'm not going to bother going to Desmos, but if I did, you would see something extremely similar to this. Oh, I also should show my my horizontal asymptote right there. Yeah, a lot of stuff going on there. Maybe this will be simpler. Just negative x squared. So I'm going to sketch that. Has a vertex at 0, but opens down. So I can show these 5 points quite quickly. All right, what's the reciprocal of this? Again, first deal with where my outputs of I of x are 0, which means an x-intercept. And there's only 1 right on 0, 0. So I know there's going to be a vertical asymptote going right down the y-axis. I know 1 over I of x is going to be invariant here and here, because again, that's where the outputs of I of x are -1. And again, 1 divided by -1 is -1, not changed. So I know my graph of 1 over I of x will go through those points. And I know it's never going to touch the x-axis. And so it must look something like this, where it shoots down like this, and then the same sort of idea of just going the other way around over here. And again, I really should show the horizontal asymptote as well. There you go. So again, what I sketched in blue is 1 over I of x, or 1 over minus x squared. All right, so what if I just give you a graph of a function and sketch the reciprocal of it? Well, that's actually, I think, in many ways easier than we just did, because I've already sketched the first part of the function for you. So again, what you have in blue here this time is f of x. It doesn't actually matter what the equation is. We could figure it out pretty quickly. It's a linear function, I can see. But if I just want to sketch the reciprocal of this, well, again, first thing I would do is pay attention to where this function has an x-intercept, and there's only 1 right here. So I know there's going to be a vertical asymptote right there. I'd pay attention to where the reciprocal is invariant, which is mean where the output is -1 or +1. I know it's never going to touch the x-axis, because 1 divided by a number will never equal 0. And now I have this sort of structure to work around, so it must look something like this. There we go. So what I've just sketched in red quite quickly is not f of x, it's 1 over f of x. It's the reciprocal of f of x. And I'm not saying anything I'm doing is easy, but it is getting relatively quick. And again, it all comes down to understanding why this first graph looked the way it does. Why we have these horizontal vertical asymptotes. Why it starts to suddenly shoot up infinitely high. And which, again, we have kind of visualized here in our table. As you divide by numbers really close to 0, you have this rapid change in what the outputs. So the last question, oh, no, I forget what I have to do here. This question here, sorry, it's not the last one. Second last question, I think. Yeah, so same idea here, though. So I'll do this quite quickly. This is, again, is the graph of g of x. I want the reciprocal of this. So again, I know there's going to be 2 vertical asymptotes just by looking at this, because the function has 2 x-intercepts. I know, again, there's going to be a horizontal asymptote. I know there's going to be invariant points here, 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 and here. I also know this point, the vertex of my quadratic function, which is at -4. The reciprocal of -4 is -0.25, so I know at that point my reciprocal function is going to be about right here. And again, I did that quickly because we did something so similar. And now I can just kind of piece this together. I know the middle part must look something like this. And I know the outside parts must look something like this. And so this particular function had 4 invariant points, because the quadratic function had 4 points where the y value was either 1 or -1. All right, so now we have our last problem. Other way around. I give you the reciprocal. You want to think what was the original function. This is the reciprocal of what, essentially? Well, what can I see here? I can see there's a vertical asymptote at -2. And I can see there's a horizontal asymptote on the x-axis. But that doesn't do me much good because all of these have had that. I can also see that, well, actually, maybe before I go on, if I know there's a vertical asymptote and one vertical asymptote only at -2, that means I know the graph of f of x, because again, what I've given you here is 1 over f of x. But we want to figure out what is f of x. So we're trying to figure out, well, I know fx must have one x-intercept right there. And I know there's an x-intercept there because I can see there's a vertical asymptote at +2. And I know there's only one x-intercept because I don't see any other vertical asymptotes. OK, so I know my function of fx goes through there. What else do I know? I know it also must go through here and here because these are invariant points. Same thing works backwards. If my reciprocal function goes through 1 or -1 somewhere, then those must be invariant points. That means my original function, f of x, must have gone through those points. So already I'm getting a sense of what this must roughly look like. I have 3 points. However, what may be even beneficial is to look at maybe this point right here or this point right here. I don't know the exact y coordinate, but I know the y coordinate looks like it's about, it's not a half, about a quarter. Which means the graph of f of x must be the reciprocal of that, about. And what's the reciprocal of a quarter? The reciprocal of a quarter is 4. So my reciprocal function probably went through somewhere around here. And it's symmetrical, so somewhere around here. And again, if that seems kind of strange, just keep in mind, if I look at it the other way around, that point there has an output of 4. The reciprocal of 4 is a quarter. That's what it looks like. And with these 5 points plotted, it sure looks like this is the graph of x squared, but translated a couple units to the right. So that sure looks like this is the graph of x minus 2, all squared. That's sure what it looks like. All right, so like I said, for this course, a small lesson, but really important going forwards. These sort of functions and these things called asymptotes, vertical and horizontal asymptotes, we'll start to see a lot in the next course and future courses. So it is while it's a small lesson for this course, please don't underappreciate its importance going forwards. But yeah, it doesn't really connect to absolute value so much, or at all. All right, and I'm all done.